All right, last time we started our discussion of geometric transformations. We talked about several different types, actually. In particular, let me actually go to our Venn diagram because it had all of them on there. We talked about these things called transformations that simply moved points around on a real number graph kind of a thing. We had, and transformations are bijections. So do you know what the word, we didn't actually talk at length about the word bijection last time. Do you remember what the word bijection means from any other classes you've had? Yep, onto and one-to-one. And for those who were in my office this morning, we actually had a discussion as a reminder of what onto and one-to-one means. One-to-one means that there's this relationship that takes everything in the domain to one element in the range, and onto means that everything in the range has something mapped to it. So we've got bijections and transformations. Hey, Hannah, if you have your homework, I'll take that. Collineations. So collineation is also a transformation. It's embedded inside of the circle, but it also preserves incidence. So when it moves things around, it does so in a way that if something was on a line to begin with, it's still on the same line it was on already before. A point that was on a line is still on the same line. Automorphisms preserve incidence. So they're bijections. They preserve incidence, and they also preserve betweenness. So if you have a point between two other points on the line, it will still be between two other points on the reflected line. And congruence. And so you guys are doing some things with congruence in your homework, proving things that were congruent to other things actually were preserved under, in particular, a reflection, I think is what you guys did. And then we have motions in the middle. Motions or isometries preserve incidence, betweenness, congruence, and length. And then you had a homework assignment where something wasn't preserved with length because you actually did one with the dilation as well. So it didn't ask you to preserve length, but it did show that you were supposed to show that it did preserve congruence when it actually was applied to a particular point or line set. All right, so this is where we left off last time. We talked about one in particular. The one we talked about are reflections. And you had a homework assignment about reflections, but reflections is where we left off. And we are going to pick up there. And Hannah, you missed it, but the homework that was for due today is the last one. There's no more homeworks. We just have our last two projects you guys are working on. So, all right, lemma. Lemma 9.1 says the following. It's pretty good. If an automorphism of neutral geometry fixes 2 points A and B. Then it is a motion and fixes each point of line AB. So we've already seen one type of transformation that does this. A reflection would do that. A reflection is, in fact, a motion or an isometry. It does have a line where the 2 points, if you take 2 points that are fixed on this, in a reflection, they would have to be along the reflecting line, which is the axis. So a reflection is an example of that. We're going to very quickly encounter another one. I don't know if it'll be today or tomorrow. I can't remember where it falls in our notes. But if you did a half-turn rotation, the same thing would happen. Is you'd have the same kinds of things where all the lines, all the points would not all be fixed. The line would be fixed is what I was actually thinking. So you have a line fixed in that scenario as well. So rotations can also fix lines just like a reflection fixes a line. Not the points, but the line. All All right. Lemma 9.2, another one about automorphisms, actually. If an automorphism fixes 3 non-collinear points, then it is the identity. We're going to try to prove it on this slide. If we run out of space, we'll shrink things up. So we're going to suppose that we have 3 fixed points. And of course, non-collinear. All right, so our previous lemma said something. So by lemma 9.1, all the points on AB that is line AB, and line AC, and line BC are fixed, right? So now we not only have 3 points that are fixed, we have 3 lines that are determined by those 3 points that are also fixed. So now we're going to let D be any point not on these lines. And we're going to let E be a point on AB such that it's between A and B. By Pasch's theorem, way back on page 114. Line DE now meets another side. I'll draw a picture of triangle ABC. All right, so here's A, B, C. Here are the lines. Whoops, not that one. There we go. There's line AB, line AC, and line BC, roughly speaking. And we've got point D somewhere. Doesn't really matter where we put it, but we've got point D here. Let's say it's here, and there's a point E between A and B. And if I connect D to E, no matter where I moved D around to, imagine if I moved D to over here. So if D is here, then DE is going to intersect line AC as well, right? If DE is here, it's still going to intersect either AC or BC. If it's over here, it's going to intersect BC, right? If it's over here, it's going to intersect I don't know, either AC or BC, depending on where it is. It's always, no matter where point D is located, it's going to intersect a third side of that triangle. Everybody good with that? We've talked about that, but it's been a long time. So, in that case, line DE contains two fixed points. E, which we already said, and the intersection point with the third side of the triangle. Show then by lemma 9.1 that line DE is fixed. Thus D is fixed. Make sense? So if we actually fix three non-collinear points, we have an identity that fixes everything. It's actually not moving anything around at all. All right, proposition 9.4 says if a non-identity isomorphism. All right, non-identity automorphism fixes 2 points, not just the line like I was mentioning earlier with my other example, but 2 points, A and B, then it is a reflection. Across line AB. So we can have other transformations that fix lines, but if it actually fixes 2 points on the specific line, it is going to be a reflection.
Okay, I have a question.
Yes, ma'am?
What exactly do you mean when you say fixed?
They don't move. So like on a reflection line, yeah, so if you're reflecting across this line and you're actually on the line, you don't move. You are your own reflection because you're on the line of reflection. Whereas if you're over here, not on the line, you do get reflected across the line over here. Does that make sense?
So all of this is just still for reflection?
Well, this particular proposition is coming back to reflections. The ones we were looking at before were not necessarily talking about reflections. They were talking about transformations or automorphisms in general. Yeah. So, but fixed simply means it doesn't move. So this was about lines of reflection, but there are other symmetry or other transformations that fix points as well. So the one that I had mentioned last time is, let's say, for instance, that you had a rotation. And so you were rotating about this point A. Well, if you're rotating about point A like a spinner, A doesn't move the whole time, but every other point in the plane would. Now, you could do a half turn, which just turns this line around and the line lands back on top of itself. But even in that, it doesn't fix all the points on the line, right? It moved all of them except for A. A is still the only point that's fixed. So if you have 2 points that are fixed, say like this, then the only way that can happen, what this proposition is saying, is if it was a reflection that you were doing as your transformation.
Well, how do you get fixed lines though?
Well, this line would be fixed under a half turn, right? So if I turned this, I can't visually move something on my screen for you, but if I have a line and I rotate it like a spinner on a game board, the line itself's image is the same as the line it started with. So aside from the points and their new locations, the line looks like the same line. It's in a different orientation, but it's the same line. All the other points in space moved, right? This point would actually move over here if we did a half turn. So all the other points actually physically move location away from where they originally were and away from the line, but the line itself landed, so to speak, back down on top of itself. Okay, so the line was fixed back on top of itself, but not every point on the line was fixed, just the point in the middle. Yeah. It's called the turn center, actually, and you have that on rotation. Okay, so talking about this one, proving now that it is actually going to be a reflection when we have two fixed points. From our lemmas, each point, that was a lemma point, well, let me write it down. Each point of AB, line AB, is fixed. That was lemma 9.1. It said if I have two fixed points, the whole line's fixed, okay? So we've got the whole line fixed. And no others. No other points fixed, because if it were, then it's not on this line. If it were, then we would have the identity. That was what lemma 9.2, I think it was called, said. Okay, so we've got all the points along AB are fixed and none of the other points are. So consider C that is not on AB, and drop a perpendicular from C to AB. Okay, here's our line AB. Here's point C, somewhere not on AB, and we're dropping our perpendicular. Okay, so far so good. It doesn't matter where I put C, just put it up there instead of below. We're going to call the location where it meets F. As automorphisms preserve angle measure, we talked about that last time. The 90 degrees, which is what angle, which is the measure of angle AFC, has to equal the measure of angle AFC prime. So wherever else C prime is, we would have to have a 90-degree angle when it forms our angle measure on our rotation. Okay, so far all I know is I've got this 90-degree angle, which is what lets me draw it perpendicularly on the other side. So what I've said now is C prime lies then on line CF. Moreover, CF is equal to C prime F by lemma 9.1. Thus, C prime is the reflection of C across AB. Okay. So the fact that there's automorphisms, we're preserving length, we're preserving angle measure, and so that's the only location where it could be that is distinctly different than C already, and we know that it can't be C already because then it would be preserved as an identity, and we said that it was a non-identity automorphism. All right, I think I have space on this one. Proposition 9.5. If I have triangle ABC congruent, triangle ABC is congruent to triangle A prime, B prime, C prime, if and only if there exists a motion mapping A, B, and C onto A prime, B prime, C prime, respectively. Moreover, this motion is unique. Okay, so clearly it would need to be a motion. If it weren't a motion, we wouldn't have links preserved, right? So that makes sense that we would need to have a motion in order to do this. We, in an effort to try to move more quickly through things, I'm skipping some of my proofs for us to do. You'll survive, I promise. It's okay. So a corollary to this proposition is the following. Every motion is the product of, at most, three reflections notice what it's not saying. It's not saying that you might not have used 4 or 5 or 6 reflections to do it, but it is saying that if you did it that way, there was an easier way that it could have been done with 3 or fewer. Does that make sense? We all do things the long way sometimes, and you think to yourself, I could have done that faster if I had only done, so this is what this is saying. We can do it with at most 3 transformations. We don't need, or 3 reflections, excuse me, we don't need more than that. Okay, we're actually going to define a transformation that I have referenced at least twice now. Suppose line L and M, I think it should say lines L and M, meet at point A. The motion T, which is the composition of a reflection over L, reflection over M, is called a rotation. About A. An example from algebra. When you check for origin symmetry, do you remember doing that once upon a yesteryear, a long time ago, or maybe in the Success Center not so long ago? Checking origin symmetry. So there's two ways you can check origin symmetry. One way that you can check origin symmetry is to see if the point is a reflection over the x-axis and y-axis. You can reflect one at a time. So you reflect over x, you reflect over y. Do you end up with the new point? Right? Does it reflect by reflecting over those two axes in composition? The second way that you can think about origin symmetry is a rotation, to rotate 180 degrees around the origin. The other book that I'm using also references this as a half turn. Okay, that's an example of one where you've seen it used, that a rotation can be thought of as a double reflection. A couple of notes. This rotation fixes only A. Yeah. Okay, it's going to fix only A, the point that the two lines of reflection have in common. And when we take the rotation L composed with the rotation M, and we look at its inverse, it would be doing the rotations in the opposite order. Rotation M composed with rotation L. Okay, so they are inverses of one another. The rotation's done in a different order. Sorry, the reflection, I keep saying the rotations. The reflection's done in a different order, so I meant to say. My bad. I'm gonna write that down. All right, proposition 9.6. Let L be perpendicular to M. A is the intersection point of L and M. And the transformation is the reflection of L composed with the reflection of M. Then for any point B not equal to A is the midpoint of B prime. So we'll draw a picture for that. We have to have perpendicular lines. It's pretty good. So here's L and M, and A is their point in common in the middle. B is any other point. And if B were reflected across line L, reflected across line M, and or rotated, the same thing we talked about through each of those, through the point A in the middle, we would end up having our reflection, we'll just go this way, right here. So here is B prime. Then this line that would connect B and B prime actually will go right through A, and A will be the midpoint of that line. Okay, and any idea how you might think to prove this from prior proofs or experiences that we've done? How would we be able to prove that? Triangles, yeah, that's exactly right. Do you see the triangles there? I didn't draw them in yet, but do you see where they would be? Yeah, they're going to be right here, drawn in, something like that. Okay, we would use triangles to prove that. A note about this. I've already mentioned this once before, but just as a reference, this only works when they're perpendicular. So for L perpendicular to M, this specific one, the two rotations that we just, reflections that we just did is a 180-degree rotation about A. And like I mentioned before, in that specific scenario, it's called, that 180-degree rotation is called a half turn. And specifically, it is notation-wise denoted H for half turn around point A.
Why does it require them to be
I think your reflections will not always end up being a rotation of 180 degrees, depending on where you're rotating around. I'm trying to imagine one, so let's try it when they're not. Oops. So if you're reflecting this point across the line, you would end up here, and then when you reflect it again, you'd end up here, and you wouldn't be 180 degrees from where you began, right? That's going to be the why. The angle measure doesn't work out right. Yeah. So now we've got an overheating projector. Fantastic. Okay. One more notation bit around or regarding our half turns. We write the image of P under this half turn, HA, as PA. Proposition 9.8, another one about rotation specifically, says if T is a rotation about A, and M is any line through A, then there exists a unique line L through A such that our rotation is the composition of the two reflections, RL and RM. Moreover, if L and M meet in an angle of d degrees, then the rotation is a rotation, rotation T, so T is a rotation by an angle of 2d degrees. Proposition 9.9. For a given point, A, that's better, the set of rotations about A is a commutative group. Okay, so we're just going to do a proof by discussion. We're going to talk through why that would make sense. I'm going to jot those items down just as a reminder of what it would actually need to be able to prove this. To prove that it is a group means that we have to prove that it's closed, that it's associative, that it has inverses, and it has identity, has an identity. And then what this actually says is not only is it a group, but it's a commutative group, so we also need to prove that it's commutative. Okay, so these first four are to prove that it's a group. The last one will prove that it's a commutative group. So let's think through this. We've actually already done this one out loud before too, about what happens when we have rotations. So remember, closed means that when I follow two of these transformations together, I get the same kind of transformation. So if I rotate something and then I rotate it a second time, is that simply another rotation? Absolutely, right? So if I rotate something 45 degrees and then I rotate it 30 degrees, it's the same as rotating it 75 degrees to begin with. Okay, so two rotations done consecutively are simply another rotation. That's closed. Associative, the order of my rotations. So, because I'm going to lose track of my numbers real quick, if I did a 30-degree rotation, and then I did a 40-degree rotation, and then I did a 10-degree rotation, would I get the same thing if I started with these parts and did them first? If I did a 40 and a 10, and then I did the 30, would it be the same thing? Yeah, it would be the same thing. And all in all, it would be still 80 degrees rotation for this, right? Inverses. Does every rotation have an inverse rotation that takes a point sort of back to its original location? Yeah, even if we fix our rotations to go from 0 to 360, and I need one of them to be open-ended, I'll use it right here. Let's go like that. So an identity, what would be the identity rotation of 100 degrees? 260, exactly. And the reason it would be the identity is, I'm sorry, the inverse, is because the identity, which is what I meant to say, the reason it would be the inverse is because the identity would actually be a 360-degree rotation, right? So your 260 that you mentioned, my 100 that I started with, add up to 360, which is the identity. So why is this commutative? Why, I mean, not why, but we need to verify that it is commutative. Is this commutative? If I do a 30-degree rotation, then I do a 45-degree rotation, is it the same as doing a 45-degree rotation and then a 30-degree rotation? Yeah, absolutely is. So all of these things are very quickly, viewable when we're looking at them. So we've checked off all of these. So we're done.
What's the difference between commutative and associative?
Associative has 3 elements. So if you remember, like from the real number system, I'll use addition as an example. If you do an associative property, it would look like this. So on the left-hand side, you would do the B plus C composition first and figure out what that is, and then you would do the A composition with the B composition, with ours example. And on the right-hand side, you do the A and the B composition first, and then you'd follow it by composition C. Okay? Whereas commutative actually would say that when I add A plus B, that's the same as adding B plus A. Okay, so you're doing them in a different order. The order is actually different, not the grouping of them. A note about this. Rotations about different points never commute. Okay, so it's unique that we talked about on the last one that it's about the same point A. A is still the rotation center or the turn center that we're talking about, and not a different turn center. All right, third type of transformation. So what have we done so far? What are our transformations? Rotations, reflections, good. We've got a new one. Our third type of transformation today is a translation. So suppose L and M have a common perpendicular. The motion which is a composition of 2 reflections, RL and RM, is a translation and what that means is it shifts points along the direction of the common perpendicular from M to L. So here's L, M, here's their common perpendicular. So if you had a segment right here, actually we'll draw the whole triangle in. Why not? Hang on. I'm just trying to make it look scalene. Okay, so here's our triangle, original. Hang on. Draw it originally over here. You don't need to move anything right now. I will. Oh. Okay. Because if we're up at my L and my M. Okay, here's A, here's B, and here's C. So if I reflect this across line M, which is what I would do first, right? You do the inside of a composition first across M. Then our triangle would come across line M and end up approximately speaking right here. It's a little bit smaller looking. Pretend like it's not for the moment. Just humor me. Okay? So this is A, M. This one would be C, M, and B, M. And then if I reflected it over line L after that, I'm going to cheat this time. I would end up over here, approximately anyway. And these points would now be A, M, followed by L, B, M, now reflected L, and C, M, reflected L. And what you notice is what it really looks like is that this point A simply shifted to the left. Point B simply shifted to the left, and point C simply shifted to the left, as did all of the segments contain, connecting them. Okay, so it's a transformation, a translation. Hang on, let me undo my message here. If they weren't perpendicular as you're doing the reflection, you're not going to see the translation happen straight across. It would be at an angle. We're just translating straight across, all right, moving it left, right, up, and down. It would still be a translation, but we're just identifying that it's just a horizontal translation right now, instead of it being a horizontal and vertical combined. Or potentially even having a rotation involved if your angles weren't 90 degrees. They might actually have a rotation in there too, and rotate the triangle's angle instead too. Proposition 910 let T be the transformation RL composed RM if Q lies on T, T is the common perpendicular, then Q prime is double the length of AB, if P does not lie on T, then P prime is double the length of AB, if the plane is Euclidean, P prime is actually greater than double the length if it's hyperbolic. Right, so much the same picture that we started with before, or on the last problem. Here's L, here's M. And we have a transversal, a common perpendicular down here. T. The first one is Q lying on T. So we're going to put Q here. So if Q is here, then QM would be over here as it's reflected. And when it reflects the last time, the final image, we'll just actually call it Q prime so that I don't have to do that ML notation like I did in the last one. Would be over here. And what happens is that the length gets doubled from what it was before. Q, well, let me write it down. I'll highlight it. Where'd you write it once? Here, Q prime, the length of the original Q, and the Q prime is double the length of A to B. Sorry, I didn't mark my A and my B. Here's A, here's B. And hopefully you can kind of visualize why that's happening. B is actually the midpoint here, right? So you've got it doubled, and then A is the midpoint over here, so you have that doubled as well, so you've got double the length. The same sort of thing happens off of the transversal, but you have equality in Euclidean geometry, and you have an inequality in hyperbolic geometry. So if P is, say, up here, whoops, P, and it gets reflected and reflected again. So here's P prime in this case. Like that. Then in Euclidean geometry, we've got parallel lines that I just drew, right? Right, because these are reflections. Reflections are creating these 90-degree angles, yes? So in Euclidean geometry, we've got all this kind of cool stuff going on, and we have parallel lines. But we don't have, if I put those 90-degree angles in, clearly there's not a rectangle here, because then in hyperbolic geometry, rectangles do not exist. So these parallel lines don't have the same features, and so you actually end up with an inequality in hyperbolic geometry. But it's greater than, it's bigger than the doubling of those lengths. Corollary to that, if a translation has a fixed point, then it is the identity motion. Hope that makes sense, right? Translations are supposed to shift everything left, right, up, and down. That's the idea. So if you've shifted everything left, right, up, and down, and you have one point somewhere that did not actually move, then none of the points moved. So it's the identity. Proposition 9.13. Let T be a translation along a line T if the plane is Euclidean then all the invariant lines of T are T and all lines parallel to T. If the plane is hyperbolic, T is the only invariant line. I have, oh, sorry, there's a couple more sentences on the next sheet of paper. To clarify this, since there are no other common perpendiculars, to L and M. That's where my picture last time was falling apart, because I was drawing two common perpendiculars, and I was talking about the fact that we can't do that because we had a rectangle forming if I do. So I haven't used this word, I don't think, in class, but perhaps you've heard it before, invariant. Do you know what the word invariant means? Another math class anywhere? No? Okay, so this is kind of along the lines of your question earlier, Shana, about the word fixed. Invariant means it doesn't change. Now the points may change, but the line is still the same line. So when I was talking about my line under my half turn being fixed, the line can be called invariant because the points themselves are not fixed. So if you imagine, I'll just go back to the picture I have before here, shifting along this line T. If you shift everything left or right along this line, then any line that's parallel to line T gets shifted left and right, but it's still the same line. All the points moved, but they just moved along the same line, right? They're just further along the line they were before as you shift left and right. Obviously, if you had an image that looked like this, you know, it moves like this, or vice versa. Actually, I started on the wrong side from where I was drawing my pictures from before. It moves from here to here, and it shifts, but it's not doing it parallel because it wasn't parallel to start with. It shifted to the left. I mean, that's fine. But the lines themselves are what we're talking about being parallel. So if I have a line in Euclidean geometry, this line, and it gets shifted to the left, looks like it's the same line. Visually, it doesn't look any different. The points are in different spots, but the line itself is in the same location. Okay. I think we'll do one more definition, and then the next one's a lengthier discussion, so we'll pause after this one. So, definition to end on. In hyperbolic geometry, L and M can be parallel without having a common perpendicular. And does anyone know what kind of parallelism that was called? There's two types of parallelism. There's divergent and no, asymptotic. And that one. And this one's actually asymptotically parallel. That's the one this one is. So this is asymptotic. In this case, a transformation, or a translation specifically, of two rotations, I didn't say rotations, reflections, I did say rotations, I mean reflections. Reflection of M followed by reflection of L is called a parallel displacement. And when we move back together, we're actually going to look at this idea inside of the Klein model, one of our models that we've done before, and see how that affects things in terms of these transformations.